Welcome to my channel, everybody. This is the chapter about induction method, and this is the second video. This is the second video for induction, but in my first video of induction, I have asked to all of you saying that there is the follow to the three step. That is what the first step was for the statement is true for n equal to 1, and the second step would be followed by the let us assume, okay, and the third step was that the statement is true for n equal to n plus 1, okay. But see this question here, not needed to follow the three step. There is only the follow the second and last step, okay. And students, see carefully, these problems are taken from the book of I.S.C, okay. And see carefully this problem. I think there is a 10 problem, 9 problem, okay, but not needed to follow the three step here. And see here, given that if if 2 to the power 2n minus 1 is divisible by 3, it means it is given that, okay, that is 3k, where k is an integer, positive integer, it means natural number, okay. So its value sort we can find it easily. 2 to the power n is equal to 3k plus 1, where let us assume this is a one condition. And now we have to show this figure is also divisible by 3. So let us take a figure here is 2 into 2 to the power n plus 1, and this is here minus 1, and that is equal to 2 to the power 2n and 2 to the power 2 here and minus 1. So from 1 we can substitute here the figure 3k plus 1 into 4 here and minus 1, and multiply by 4 here, then 12k plus 4 minus 1, that is 3, and take a common 3 here, then you get 4k plus 1. So since as k lies an integer for a natural number, so 4k plus 1 is an also natural number. So it shows that the given expression, this is divisible by 3 here, okay. So it is divisible by 3, okay. And now see, so see for the question number 2, okay, also be written here the given expression is divisible by 3, okay. The statement should be needed here. And for number question 2, and given that is 2n plus 7, okay, this is n plus 3 whole square, it is given. And now show that this figure is less than n plus 4 whole square, okay. Now left hand side is this plus 7, and that is 2n plus 2 plus 7 here, and in place of that 2n plus 7 plus 2, okay, and we have put this value in figure, okay, this is the more this is more figure, this is the value is more than the 2n plus 7. In place of 2n plus 7 we substitute the n plus 3 whole square, so on the right hand side be more, okay, so this is whole square plus 2. So see the condition here is we have to show on the right hand side is n plus 4 whole square. So follow the condition here, like this is n plus 3 plus 1 and whole square. So here is n plus 3 whole square plus 2 into n plus 3 here plus 1. So we added this term. If we add it on the right hand side, actually here is 2, so we added here 2n plus 4 plus 1, okay, on the right hand side. Then we get the whole square pattern. As see on the right hand side there is more, so again it's more added to the sum term, okay, on the right hand side to the inequality, that is here, okay, this is here we added 2n plus 4, actually 2b are more, okay. So this is n plus 3 plus 1. So this is equal to n plus 4 whole square. Therefore we can say the condition is 2 times of n plus 1 plus 7 and is less than n plus 4 whole square is proved, okay. And now I want to show the question number 4. Actually students, see, this is the book of Asian, the page number 269, and it is the marks 2. It is the there was the some pointer mentioned marks 2 question, marks 4 question, marks 5 question, okay, and this is the part of marks 2 question, okay. So now we have followed the question number 4 here. See, there is a 1 into 1 factorial, 2 into 2 factorial, 3 into 3 factorial, okay. It is given that 1 into 1 factorial plus 2 into 2 factorial plus 3 into 3 factorial and dot n into n factorial, and that is equal to given that the n plus 1, this is minus 1, okay. Now we have to show the more one, this is the last term here, you see again, and this is the last term here which is given, but the another term, that is the nth term, we added, okay. So in the induction, which I asked to follow the 3 steps in my first video. There was the last step, we have always increased the one term again, okay. So this is the final step actually. We have to show 1 dot 1 factorial, 2 dot 2 factorial and 3 dot 3 factorial and dot to n dot n factorial plus n plus 1 dot n plus 1 factorial, okay. This is factorial. From these two, this to this is the condition 1. This is 1. Okay, we have substituted here, that is n plus 1 factorial minus 1, and this also a more term, that is n plus 1 into n plus 1 factorial. Okay, students, see carefully and take a common n plus 1 factorial n plus 1. Then we have that is, okay, so here left here 1 and here is n plus 1 and this is minus 1. So here is n plus 2 and dot n plus 1 and factorial. This is, students, 5 into factorial 4, and that can be written as factorial 5 here, okay. So that's why this is n plus 2 and factorial n plus 1. So we can write here n plus 2 factorial and minus 1. See, this is proved here, okay. Okay. Now question number 5 also same as like question 1. So repeat again. See what happened. So I have question number 5, and that is divisible by 11. So I can write 10 to the power 2n minus 1 plus 1 is equal to 11k, where k is a natural number, k lies on the natural number. Then you can say the expression is divisible by 11. So the same as question number 1, just repeat here, okay. Now we have to show this is also divisible by 11 actually, and then you take in the figure here 10 to the power 2n plus 1 and plus 1 also, and see this expression is compared with this. So this expression is converted term of that, okay, like 10 to the power 2n. Here is minus 1 and there is a plus 1. So we product with the 10 square. Then if we added these two, then we get the first position. Okay, now here 1, and see again in this part 10 to the 2n minus 1. See, this is equal to 11k minus 1. Okay, this is 100 and this is 11k minus 1 plus 1. So that is 1100k minus 100 minus 1. This is plus 1. So 110k and this is 99. So simply take a common 11, that is 100k minus 9. So it is clear, shows that the 100k minus 9 lies on a natural number, since k is a natural number which are taken on the condition number 1. So we can say easily this expression 10 to the power 2n plus 1 is also divisible by 11. Okay, so this language should be needed to write here. Okay, now so 5 is complete here. Now follow the 7. Follow the 7. It is compared to 1 and 5 like that, but okay, see what happened. I have to solve this question. See, 11 to the power 12 to the power n and 25 to the power n minus 1, and that would be divisible by 3. It is given here, not would be, and this is here given that it is divisible by 30 if n is the natural number. So 13k. So take k as a natural number, then we can say that given expression is divisible by 13. Okay, this is given case. Okay, now you have to show the term, that is 12 to the power n plus 1 and 25 to the power n. It is divisible by 13. Okay, it is divisible by. Okay, now we have to show. So from that, see, this is either we have to take n to the power 12 to the power n is equal to or 13k minus that, and that is 12n is equal to 13k minus 25 to the power n minus 1. Okay, from this, and we can write 12 into 12 to the power n and plus 25 to the power n here. So that is 12, and in place of 12 to the power n, we substitute this figure, that is 13k minus 25n minus 1. See, this degree to the power 25 is n minus 1, so but here is n. So from this we can write here 25 into 25 to the power n minus 1. So here 13 into 12, 13 into 12k, 13 into 12k, and this is multiplied by 12 into 25 to the power n minus 1, and that is 25 into 25 to the power n minus 1. So simply we can add it and odd subtraction, subtract it from the term, like this is 12a minus plus 25a. So then you get here 13 into 25 to the power n minus 1. So we can say this is this is divided by 13. Okay, so this is divided by 13. So that is, we have to take a common 13, then we have left here 12k and plus 25 to the power n minus 1. And this is this figure, and this figure is a natural number, you can see here. So 25 to the power n minus 1. Okay, n minus 1, it is like a natural number. So it clearly says that the expression is divisible by 30. So it is 7 complete. Okay, now question number 8. This is here question number 8. This is a question number 8. Let us take up like a function like that is f of n, given that is n cube, n plus 1 whole cube, or n plus 2 whole cube, and given that this is always divisible by 9, so 9k again. So let us assume k be an integer, so you can say that given the expression is divisible by 9. Okay, now this is given. And now we have to show that this expression is divisible by 9. Okay, now f of n plus 1 whole to the power 3, n plus 2 whole to the power 3, and n plus 3 whole to the power 3 here. See, compare with this, okay, these and these are same, and also these and these are same, but in between them, so we have expand this, as a cube, but don't expand this way as we gave the same part of the given condition. So now expand this. So now n plus 1 whole cube, and this is n plus 2 whole cube, and see this is here we can write n cube plus 3n square into 3n into 3 square, and 3 cube. So from that, and this is given fn. So right here this is fn, and that is 9n square. This is 27n plus these also are 27. So this is here fn, that is 9k. This is a 9n square. This is a 27n. This also 27. Take a common 9. So that is k. N square. This is 3n plus 3. And so here k is a natural number. Therefore k plus n square plus 3n. K comma small n, natural number. 3n, this is also a natural number. So we can say that the let us assume this is f of n plus 1. That f of n plus 1 is by 9. Okay, it's proof. Okay, this is number question 8 is complete. Now follow the question number 9. This is here 9. 1 plus x to the power n, and that is greater than equal to 1 plus nx. Now show that 1 plus x to the power n plus 1, and that is greater than equal to 1 plus n plus 1 into x. Okay. See, split the power like x to the power n. It is given that the power in here, so you can explain now. And now in place of 1 plus x whole to the power n, substitute this figure. So 1 plus nx into 1 plus k here. But this expression is not equal to the previous condition, so it would be a less than, as this is a smaller term come to the left hand side, so this would be a less than, this is a greater than, but right hand side is less than. Okay, this is equal to means we have to compare with that, not these. Okay, so follow the step carefully and multiply those two factor, and then we get here like by 1, what we get here. Okay, and then by product x to the first part, then x into nx square, and c, take the common x here, so that is x into n plus 1 plus nx square. So if we eliminate this term, then we get this. So actually this is follow the more than, okay, and right hand side is less than, as this is eliminating, not eliminating, this is a cancel. Then we get here this and follow the condition. Okay, this is proof for question number 9 here. See carefully. Okay, now for question number 10. Okay, now again question number 10. It is given that f of this is here not n, this is here a. Okay, this is f of n, and given n into n plus 1 into 2n plus 1, and if n is always divisible by 6, so again 6 into k, where k be a natural number, then we can say the fn is divisible by 6. Okay, it is given that the expression is divisible by 6 here. Now we have to show that the f of n plus 1, if we find the f of n plus 1, we replace n plus 1 and we get here n plus 1. So if we put here n plus 1, then we get here n plus 2. If we put here n plus 1, then we get here n plus 3. Okay, in place of n, substitute here n plus 1, so we get this. Okay, now see carefully, compare with the term that is equal to this and this are same, so this factor will be unchanged here. Okay, now this is here 2n plus 1, but here this is 2n plus 3. So from this figure we can write like now 2n plus 1. Okay, compare with this 2n plus 1 plus 2 here. So this as a whole part multiplied by this and multiplied by 2. Then we get here n plus 1, and this is n plus 2, and this is 2n plus 1. Actually check it in 2n, n plus 1 plus 2 plus 1, 3. Okay. and multiply by 2, then 2 into n plus 1, and that is n plus 2. You can see, and these two terms are same. On the first part is given that the expression is given by 6 here. So split this part by n and 2. Okay. So n plus 1 and 2n plus 1, and this is here n plus 2, and 2 into n plus 1 into n plus 2. So multiply this part by n and multiply this part by 2. Then what we get here, and that is 2 into n plus 1, and this is 2n plus 1, and this is 2 into n plus 1, and this is n plus 2. And see, this is 6k, which is given condition. And now take a common these two part, second and third. That is 2 into n plus 1 is a common. So left here is 2n plus 1, and other is here n plus 2 here. So this is 6k. This is 2 into n plus 1, and that is 3n plus 3. So take a common 3. So 6k. So 3, that is 6, and n plus 1, and that is here n plus 1. So n plus 1. And take a common 6 again. So k plus n plus 1 whole square. And no, k or n are a natural number. Okay. Therefore k or n plus 1 whole square is a natural number. So we can say the expression is the divisible by 6 here. Okay. The expression is divisible by 6. You can say. So okay, this is complete to this video for the class of induction. Okay, bye everybody.